So we have a couple more problems to do, exercise 5 and 6. Let's start exercise 5. So on the handout it says the half-life of a radioactive element X is exactly 120 years. Part A is to determine the value of K in the formula for the function f of t equals a0 e to the kt. We are not given a value of a0. Turns out here we don't even need a value for a0 to figure out what k is. Let's look at a table of values. So I'm going to have t f of t. Now we know when t is 0, a0 is the function value. If the half-life is 120 years, that means if 120 years goes by, so this is all years here for t, we're going to have half of what we started with. So we could say that's going to be 1/2 of a0, or 1/2 times a0. We can actually use this information to set up an equation that we can solve for k. Let me recopy the function f of t equals a0 e to the kt. So I'm saying f of 120 equals a0 e to the k times 120, but f of 120 would have to equal 1/2 times a0. And that e to the k times 120 I can write as e to the 120k. Now I don't know what a0 is, and we don't care, because we can divide both sides by a0. That's sort of the magical step here. And so I'm going to have 1/2 a0 divided by a0 equals a0 e to the 120k divided by a0. Cancels here, cancels here. I'm left with 1/2 equals e to the 120k. And the only variable now in this equation, or the only unknown in this equation, is k. We can solve for k. Now, so here we go again with our process. I'm going to rewrite that 1/2 as 0.5 and take ln of both sides. So ln is 0.5 equals ln of e to the 120k. ln of 0.5 is equal to ln e cancels. I'm left with just 120k. And divide both sides by 120. We've been doing this kind of process a lot. And so ln of 0.5 over 120 is equal to k. And I need to get a decimal from my calculator. And I did this ahead of time, and I rounded off. I get a negative result here. I get negative 0.005776, and I did round off, so approximately k. And I guess that's our answer, right? Just to find the value for k for part A of the problem. So we use this little trick of the 1/2 a0 as an output value for the function equals the function with 120, the half-life, plugged in for t. And that allowed us to solve for k. All right, now let's go on to the next part of that same problem, problem 5. How much of the initial amount will remain after 60 years? So B is how much of the initial amount remains after 60 years. Okay, well what's the initial amount? The initial amount is the A0 quantity, right? If we thought of setting up a table of values, we got A0 at time t. We want to think about what function value we would have after 60 years go by. So let's see what we can say. F of t equals A0 e to the kt. Now, I don't know what A0 is. We don't have a value for A0, but we do have a value for k. A0 e to the k is my minus 0.005776. And now when I put this back into the original function, I have my variable t back there, right? So we got our k value. Don't forget we also got our t variable there. This allows us to calculate function values for other values of t, and we want t to be equal to 60. So let's plug in t equals 60. F of 60 is equal to A0, which we still don't know, e to the negative 0.005776 times 60. Okay. Now, let's see what we can say. Is how far can we go with this without knowing what A0 is? I can take 60 times this negative decimal. I can raise e to that power, and what I get is, now just for the exponential, I rounded this off. This is about 0.707. Okay. So f of 60 is approximately 0.707 times A0. We can think of that decimal times A0 as a fraction of A0 or as a percent of A0. So it's actually saying this is 707/1000ths of A0. That's really the portion of A0 that's around after 60 years, this fraction of A0. It's a little bit nicer if we write it as a percent, and I can just get a percent form by just moving the decimal point 2 places, right? Just multiplying by 100. So I'm going to write it in percent form, but fraction form is fine too. This is about 70.70% of A0 remains after 60 years. And you could even word that answer without A0. You could say 70.7% of the original amount remains after 60 years. So that's true no matter how much the initial amount is. That percentage is just, that's the percentage of the initial amount that's going to be there. All right, part C. Part C of the problem is, how long will it take an 80-gram sample? How long for an 80-gram sample to decay to, what did it say, 60 grams? Okay. Now I'm going to use f of t equals a0 e to the negative 0.005776 t, going back to the form with t. And we can think of the 80 gram as our initial amount, our starting amount. We can actually assign that value to a0. So for this part of the problem, we can say a0 is 80 e to the minus 0.005776 t. And I think here we want to know how long means how much time, how many years. We need to find a value for t when f of t is equal to 60 grams. So we're going to set the function value equal to 60. 60 equals 80 e to the negative 0.005776 t, and solve for t. So I feel very much attached to my long decimal in this problem, but the process is something we've been going through several times now. Isolate the exponential, take ln of both sides, solve for t. So here we get 60 over 80 equals e to the minus 0.005776 t. 6/8, that's just 3/4 or 0.75. Take ln of both sides. ln of 0.75 is ln of e to that power. The ln and e cancel out on the right. So ln of 0.75 is going to be negative 0.005. If I can write it down, 5776 t. So now I divide by that coefficient, that long decimal. So ln of 0.75 over negative 0.005776 is equal to t. And again, it's maybe just worth noting that even though we're dividing by a negative, the final result here is going to turn out to be positive, because ln of 0.75, the numerator, is a negative number. We got a negative divided by a negative. We get a positive. And I'm just going to write it here. T is about, I already put this into my calculator, 49.8 years. That's our answer for part C of that problem. So we got our B and our C showing here. I think I'm gonna stop, and the last example I'm just going to do is a separate video.